sure to go out, check the weather, read the news on the streetcar. On the back end, my location will be continuously updated, downloaded files will be logged, and my browsing history will be published to many different web servers hosted in any number of places. For the most part, this is my everyday routine. Each activity in this ritual shares data to third parties concerning where I am, what I'm doing, and what I'm paying attention to. On average, an internet user in the developed world will generate about half a gigabyte of data per day. As the world increasingly adopts technologies like IoT and smart cities, that number is only going to go up. And it's a lot of data, and most of it's outside of our control. So why do these companies want this data? It's fundamentally valuable. In its analyzed form, it can be used to inform smarter decisions with a higher probability of optimal outcomes. I'll give you an example. Market research has shown that people are more likely to change their more consistent purchasing decisions after a major life event, having a baby, for example. The department store Target famously leveraged this. Along with the data from their rewards program, they built a model that was able to predict whether or not a rewards customer was on track to have a child in the near future. So when Jane Doe, call her Jane Doe, she's an actual person, she purchases, let's say, cocoa butter, a bag large enough to double as a diaper bag, and dietary supplements for zinc and magnesium. Target would know to push prenatal offer survey, and this practice was really good. It drove, famously in a story in the New York Times, it drove a father to confront a manager very publicly, start shouting at him and accusing him of trying to encourage his teen daughter to have a child. And the same father would apologize weeks later after his daughter admitted to him that she was due in 6 months. So I've established that data is valuable, but it's also privileged. There's a cost to collecting data and to processing actionable information. Energy and infrastructure must be leveraged to do this, incurring an opportunity cost which prevents the same energy and infrastructure from doing other valuable work. You know this intuitively when you study for a test. Cheaters who copy answers from students also leverage the energy and experience of that student, meaning that the opportunity cost of the cheater for passing grade is much less than it is for the student who studied. So data has the potential to improve our lives and the lives of those around us. I think we can all agree with this statement. At bottom, it helps us to predict the future, to predict what others will do in the future. And as security specialists, so those of you in this room, you also know that data has the potential to make us as individuals vulnerable to harm caused by malicious actors who would use our personal data to make their attacks more effective. So what kind of harm and how bad? So you've no doubt heard the term social engineering attack. This can take the form of blackmail or a confidence scam. One particularly cheeky version I've come across is the grandparent scam. You guys familiar with this? Yeah? Okay. So I'll basically use personal data to make your narrative a little more believable and to get people to give you money. Usually the attackers in this case are committing identity theft. That same scam can be targeted at banks and creditors on your behalf. The worst cases will result in like swatting, so sending tactical teams to your house. So this is using your personal data to real detriment to everyone's life when they least suspect it. So why do we risk it? What good can come of sharing our data with others that could outweigh the risks posed by those even few who use our trust? Social programs, they can leverage demographics and usage rates to make them better. Governance decisions by our governments, they can be used to, like economic and climate change policy are usually based on mathematical models which leverage like gobs of data. And of course, the purchasing patterns like Target, that can make people a lot of money and help them develop supply chains which will make things cheaper. So how do we get the good stuff from data while avoiding the bad stuff? That's the data problem. Or to put it more concisely, how to share data as to maximize utility for the common good while minimizing its potential for harm to the individual. So let's step back a moment and try to put ourselves in the position of those who manage large data sets. These are the people for whom the data problem looms largest. Notably, they're the ones who buy de-identification solutions and determine their sufficiency for legal purposes. before I go on, does anyone have any questions? So, like any process, it relies on defining concepts and data processing technology, which I'll describe as I go through a high-level overview of a de-identification operation. So, data within a data set can be broken down into two categories, personal data and non-personal data. Other data may need protection, like trade secrets or strategy, but that's beyond the scope of de-identification. De-identification is solely concerned with personal data, that is, information associated with an identified or identifiable individual. To begin with, you need to classify the personal data within the data set, or refer to each datum as a token. This will involve describing the variable type, so whether it's a Boolean, categorical, discrete, or continuous sort of variable. In unstructured data sets, prose writing, which lacks the convenience of columns and rows, it'll be necessary to parse that data through a natural language processing engine. OWL, GATE, these are examples of NLP engines. They're both open source. There are many variations on this, but in all cases, you'll need to identify tokens as being either a quasi-identifier or a direct identifier. So a direct identifier is a token which is sufficient to identify a single individual within a data set. Examples would include a full name, a social insurance number, a primary key, basically. Such identifiers guarantee that any associated information with this datum is true and potentially learnable by an attacker. A quasi-identifier is a token which, on its own, is insufficient to identify a single individual, but serves to narrow down the number of associated individuals into a subset for which the quasi-identifier applies. So examples would include date of birth, postal code, and sex. They're still informative, and when combined, can be used to uniquely identify someone. To demonstrate their potency, there's a privacy researcher by the name of Latanya Sweeney. She demonstrated back in 1997 that the combination of birthday, zip code, and sex was sufficient to uniquely identify 87% of the population. So the next step is to evaluate the risk of the data set, which will lead to the generation of replacement values of the tokens. Whether you're taking a rule-based approach or a statistical approach, this is the point at which you compare the data set you just classified to the ideal data set, which reaches the threshold of re-identification risk that's possible. I'll speak more about the different ways to do this later, but fundamentally, the risk of re-identification is equal to the data risk, that is, the probability that an acquaintance will be able to positively identify a person in the data set, times the context risk, which represents the risk profile of the environment to which the data is shared. A public release of data into the world would present a high risk value here. Whereas a release to a privileged few in a secure building would present a lower risk value. The decision to lower context risk often results in greater utility of the data, depending on the methodology used. Finally, you replace the tokens with replacement values generated by your chosen de-identification methodology, and the output is a de-identified data set with enhanced protection and a release from liability because of its decreased potential for causing individual harm. Were this data ever caught up in a data breach, the data custodian will show the judge how they performed this task as evidence that they did everything they possibly could to mitigate the damage that a breach might cause. And this would generally reduce any sort of personal injury settlement that would result from the breach. So, any questions about that before we go on? Pretty simple. So we've discussed the data problem and its implications. I've described to you at a high level how one goes about processing a raw data set into a de-identified data set. So now I'm going to go over some of the de-identification methodologies which vary greatly in terms of complexity. These solutions are valuable to those who collect and use data because, as I mentioned, it provides legal cover, a partial to full release from liability in the case of data breaches or decisions based on privacy law. So the general idea is to reduce the harm to an individual by separating the individual from the knowable facts in the data set. The individual can be represented in the data set by either a single direct identifier or a collection of unique quasi-identifiers, as I mentioned before. The knowable facts is personal information. They're facts associated with that individual which are potentially knowable by an attacker. To test the effectiveness of the various de-identification methods, computer scientists test them with re-identification attacks. This approach mirrors what's done in the field of cryptography to test encryption algorithms that have been developed over the years. The fundamental philosophy is basically only the strong survive. There are three broad models for re-identification attacks. The most likely to be successful attack is known as the Prosecutor Attack. The goal here is to link a record in the dataset to a real person. It assumes that the attacker knows acquaintance-level information about the target and that the attacker knows the target exists in the database. On its own, the knowledge that a target is in a dataset is very informative. Creeping your ex through Facebook would be an example of a prosecutor attack. Journalist attack is similar. By the time this attacker is missing this time the attacker is missing either a knowledge of the target or the knowledge that the target exists in the database. Crucially, the attacker is missing one and only one of these factors. And finally, the last model is known as marketer attack, which is probably the best model to apply to the Jeff Bezos story we went over earlier. The goal is focused more on re-identifying as many people as possible from the dataset with a disregard for false positives. This is the kind of attack exemplified by, say, robocalls or telemarketing scams. So the first approach to de-identification is to apply a rule, and that rule would be, if there's data for potential for harm, hide it. The trouble here is that different jurisdictions will classify personal data in different ways. In the United States, the Health Information Portability and Privacy Act, known as HIPAA, it governs the sharing of health data. The legislation provides us with a list of 8 clear data types. If you match these, you're in compliance. Other jurisdictions, such as the EU, they classify personal data a little bit more abstractly. From the data processor's perspective, this approach to lawmaking makes it very difficult to provide data utility by encouraging a more conservative approach that is skewed towards data protection. So the simplest method is redaction. I'm sure this is something you all know of. Redaction works by obscuring the data tokens so that they're unreadable. This can be done in many ways. The most popular way is to cover the tokens with a black box, effectively destroying the direct identifiers. This is intended to break the connection between identifiers representing a person and the learnable personal information in the data set. This method's pretty old, easy to implement, and easy to defend. To this day, it's still used in government documents, specifically those released through Freedom of Information requests in this country. In this sort of application, redaction can be used to obscure confidential information as well, like trade secrets and strategy, as well as personal information. So why is this technique insufficient? So de-identification as a process is largely reliant on humans or increasingly machine learning. With either approach, there's a certain margin of error that can be expected, meaning that some tokens containing personal information will be revealed. In the case of redaction, missed tokens, which are left unhidden, are obviously so, and they are guaranteed to be true, and each represents a privacy breach for legal purposes. The other shortcoming of this method is that redacted data sets are often not very useful for analysis when correctly applied to quasi-identifiers. They have low utility due to the lack of quantitative data like demographics, dates, and measures. So an improvement on redaction is pseudonymization. This method takes direct identifiers and replaces them with reasonably believable replacements. On the left, you're going to see the full names of our data sets, of our data subjects, changed to false but more believable fake name N. I chose fake name just to highlight what I've done graphically, but in reality you'd use a much more believable proper name, chosen at random. The idea here is that pseudonymization breaks the association of direct identifiers with any quasi-identifiers, the intent of preventing attackers from learning anything new. Now, I mentioned earlier that direct identifiers are not the only way to positively identify individuals in a data set, and how groups of quasi-identifiers can collectively and uniquely identify a person. Let me show you how that works. So we take our present data set, we pseudonymize it, take another data set which you presumably acquired legally. So the data on the right is not much unlike the voter registration list that you could purchase in the United States. In Latanya Sweeney's example, she purchased this for about $20. And you match them based on sex, birthday, and postal code, and you notice that when combined, these fields function like a unique direct identifier for each record on our data set. Linking the two data sets allowed the attacker to deduce the full name for each subject. The first table, which was pseudonymized, therefore learning the true race, sex, age, height, postal code, and rough geographical location of each subject. So same thing with our unstructured data set from the previous example. Pseudonymize it. Now we'll switch hats and become the attacker. We'll find more or less publicly available data set to perform our data link attack. We'll match our original unstructured and pseudonymized data set on date and location, and now we know what our victim's face looks like. So now you can increase the protection afforded to data subjects by choosing to broaden your rule to cover quasi-identifiers as well as direct identifiers with false values. This protection comes at a cost to utility, and you'll only ever get a subjective feeling of how much you're reducing the risk of a successful attack. You will, however, reach compliance in some jurisdictions, for example, HIPAA and its 18 data types. And sometimes it's all you're looking for. Like all rule-based approaches, this is a pretty cheap implementation. It can be a little bit more effortful than Redaction, since it takes a little bit of time to create realistic pseudonyms and properly reformat text. Like Redaction, it's also error-prone, but the lifelike replacements allow missed values to blend in with the cleverly designed pseudonyms, effectively hiding them in plain sight. So I've talked about the rules-based approach, but there's another way to de-identification. There's a statistical approach to de-identification, which involves optimizing the relationship between data utility and data protection. Modeling the data problem as an optimization problem is ideal because of the inverse relationship between data utility and data protection. Intuitively, we have some sense of data quality, and I'm calling that utility today. Consider credit card information that's been encrypted. In this form, it's not especially useful to an attacker without learning more information, like a key, low utility, high protection. Conversely, in its decrypted form, it's useful to an attacker precisely because it is unprotected and immediately actionable, high utility, low protection. For an optimization model to work here, we need real numbers to represent at least one of these properties. By choosing utility and assuming that it is equivalent to Claude Shannon's definition of information, we can use his information theory to convert this property into a continuous variable known as bits. These bits, or Shannons, as they're known as Shannons, represent the entropy of a variable for a given value. That is, the degree to which the value deviates from being randomly distributed. Fundamentally, it all boils down to the answer of a yes or no question. And I'll show you what I mean. So I'll give you an example where we're categorizing individuals based on biological sex. Assume, if you will, a 50% chance of being male in a population with an equal number of males and females. If you were to ask that question to each member of the population, you'd quickly find that you would need to ask that question once on average. Knowing the biological sex is worth 1 bit. Let's expand on this out of another variable. Let's say that each group of males and females was split evenly, that's 50-50, into those individuals with brown eyes and those without. Using only yes or no questions, we need to ask 2 questions on average. Each question would be worth 1 bit. Collectively, both questions would be worth 2 bits. So if you were to change this variable to one with 3 possible values, rather than just the 2, say hair color, dark blonde, and red, you'd find that you need to ask 2.4 questions on average to each individual to properly classify them. 2.4 questions, 2.4 bits. There's a logarithmic function that's going to allow you to derive this value. For a given value of a given variable, the bits of information for that value is equal to the negative base 2 logarithm of the probability of that value appearing in the population. Essentially, you flip the signs in the exponent to which you must raise the value of 2 in order to get that probability. This unit of information is used to determine the risk of re-identification as well as the risk threshold. There are many ways to calculate this risk. Many of them depend on some arguably hand-wavy psychological variables like average number of acquaintances or the knowability of facts for each acquaintance. This is a very broad and contentious topic, so I'm going to leave the risk calculation aside and focus more on how data gets changed statistically. The first statistical method I'm going to describe is Epsilon differential privacy. Before I go on, does anyone have any questions about the... Okay. So, Epsilon privacy. This technique can make a data set statistically safe from attacks by replacing a subset of the personal data within a data set with randomized data. It works kind of like hash sorting. A sample of data is selected at random, and their values are randomized from the set of all possible values. The selection is made by an algorithm which works something like this. So consider a population who completed a simple survey. Do you smoke? You may or may not, this may or may not be information you want to go public, so it gets de-identified. For each response, a fair coin is flipped. For 50% of the records, the result is heads, and the true value of the survey question is kept. For the other 50%, the flip is tails, and the value undergoes randomization. Figuratively, another coin is flipped. Heads, and the value is set to y, tails, and the value is set to n. Now this is a simplified example, but you notice how 50% of the records are determined randomly, yet you can expect 75% of those records to be true, even if you couldn't point out which ones. There are multiple algorithms that can do this successfully, although they tend to make their randomizations based on something called a Laplace distribution rather than a simple coin flip. I won't go into that. This method is great because it allows you to run a big, large data set through a simple function with an effective result. It shines within big data implementations, making irreversible changes but preserving trends. But this is also the biggest weakness. This method also produces low utility in small data sets due to resolution issues. Within a small sample, the randomized salt really messes with the analytic trends, producing garbage results. There's an analogy for this. Consider the small data set of red and white pixels. Running this low resolution HART through an epsilon differential algorithm, pixel by pixel, is going to render the image unrecognizable. But in a much larger data set, a picture with much higher resolution, those changes are going to be less noticeable, and you're going to be able to make out objects like rocks, shrubs, bridges, etc. So the second and final statistical approach is K-anonymization. Any questions about epsilon differential? Okay. K-anonymization allows one to manage the quantity of information present in a data set for a given individual. This is achieved by building profiles for each individual, quantifying their overall information, and replacing overly informative values for individuals with progressively broader generalizations. This method serves to increase the size of the group which shares the value for a given variable. The K in K-anonymization refers to the size of this group. To illustrate, let's consider the game Guess Who. It's a game where you try to discover your opponent's selected person with a series of yes-no questions, so it's very well suited to information theory problems. The first one to guess their person correctly wins. So within this population of individuals, 4 people have mustaches, 5 people have beards. You'll recall that the bits indicate the degree to which the value deviates from being randomly distributed. So the 4 for which has mustache equals true, that's worth 2.6 bits. And for the 5 for which has beard is true, that equals 2.3 bits. And for the poor fellow for whom has mustache and has beard equals true, that information collectively is worth 4.9 bits. Now, you should know this calculation is a bit generalized and crude. There's a few more things to consider. For example, having a beard or a mustache implies maleness, which would shrink our population and drive up the bit values. You can get as complicated as you like, but I just want to keep it simple for today. So if we decide that our risk threshold is under 2 bits, and that the informativeness of the Boolean variable has mustache and has beard is too much, the K-anonymization approach allows us to merge these 2 groups so that K equals 9 by generalizing to has facial hair, a value worth a mere 1.4 bits. So this technique represents an improvement over epsilon differential privacy for smaller data sets. It can be employed on large data sets with restrictions. Furthermore, you can prioritize fields with a greater analytic value over those that are less less important, but still informative. In my previous job at IQVIA, we used this method on clinical trials for drugs, which would have samples probably between 9 and 100 people. K-anonymization is probably better for that, but if you had sample sizes of 10,000 or more, Epsilon differentials where the clients tend to go. The downside here with K-anonymization is that it only works on static data sets. It's difficult to apply the method to continuous data streams and achieve a satisfactory result. And because of this, de-identifications performed with this method usually contractually have to insist that data linking is prohibited. It's a bit of a cop-out, frankly. Doing such data linking would add further bits to each individual's profile in the data set and invalidate the risk calculations underpinning the generalization decisions made to the field. For example, has facial hair. So that pretty much covers what I'd hoped to talk about today. We talked about the data problem, I described how data sets get processed when implementing de-identification, and I gave a high-level description of several dominant de-identification techniques. I'd like to thank Jason and Nick for having me today, and with that, I'll open the floor to any questions you may have.
So I know orgs love to hold on to data once they've collected it, right? Have you experienced that, like, after the de-anonymization process, an org is still tempted to sort of hold on to the original data set as like a backup? Yeah. And can you talk about your thoughts on the risks of that?
Well, usually my bailiwick is largely privacy governance, and as a consultant, we try to discourage companies from holding on to data just for fun, because it represents a liability for lawsuits, because the longer it sits there, the longer it's open to attacks. Usually de-identification it's very expensive, and they won't do that just for kind of hobby data sitting around. What they use de-identification for is when they want to share data for secondary purposes. So in the case of the clinical trials data that I spoke about earlier, the idea of de-identifying it was so that they could put it onto a portal in the European Union, and that opened it up to all academics everywhere, whereas before it was de-identified, it had to stay within the pharmaceutical company, and they couldn't share it. For example, a company that sells Viagra, the people who participated in that wouldn't be too keen if their data was shared on a public portal, because it has a lot of intimate information. So I hope that answers your question.
Yeah, so you're saying they're fine holding on to the original data set and willing to accept the risk, but it's when they won't share it. That's when they would typically go through a process.
Sure, yeah, that would be it. Or if they want to decrease liability, like if you're selling a de-identification solution, you're going to try to sell it to them in every possible reason why. But yeah, it's largely for when they want to share it. And also now, especially in the EU, it's increasingly the case that when you give consent for your data, you're also consenting to the very specific uses of your data. So if, let's say, Google has an EU citizen in their database, and that citizen has agreed only to provide it for purposes of delivering email content, then Google can't just unilaterally say, oh, I'm going to use it to determine analytics for selling them some sort of widget. They have to go back to the customer, get them to sign a consent form, and that's basically impossible. Doing a de-identification operation on a data set makes that data set no longer personal information. So you get to do whatever the hell you want with it. There's no privacy laws, there's no threat of lawsuit, because you can basically go in front of the judge and say, well, we de-identified it, according to your rules, it's not PI anymore. So. Anyone else? Questions? Yes?
Do you mind going over again what you meant on the pieces of data have a certain length paperwork?
Sure, yeah. Mm-hmm.
Yeah, like, I just didn't quite understand, so that certain pieces have higher bit weight than the other.
Correct. So I think you can get this notion intuitively. So if you have a group of people who are, let's say you have a population, a very homogeneous population of white males, age 37, and there's like 50 of them. One person out of that homogeneous group is some sort of special case. Say they've got like a big horn on their head. If you have horn equals yes, that's going to be worth more information. Whereas if horn equals no, that's really not going to tell you much about who the record is actually referring to.
Oh, sorry, so it's just the value measure. Just use the value certain so it's
What about it?
that they just use the value certain pieces of information in the context of the meditation.
Right.
That's all.
No, we use the value to run through the risk measurement operation. So I'm not sure I quite understand the question.
It's okay, thanks.
Anyone else? All right, great. Well, thank you very much for having me. It was nice to come back to share. So, thank you.